Perfect.
All right. So I might actually, let me just share my screen here. And then,
Oh, and also maybe I should mention, are you fine for us to post this on YouTube at the end? We have like a YouTube channel with the seminars.
Oh, yes, except I didn't get my paper out on the archive yet. So I don't know if I qualify for the YouTube channel, but I will get it out in the next week.
Okay. Yeah, there will be some time before we will post it anyway. So
okay, great. Okay. So, okay, now you probably see my presenter view, huh?
Yeah.
All right, now you see.
Still.
Oh, no, you still see, yeah. And now?
Now we see the full thing.
Yeah. Okay, great.
Yeah.
So should we just leave it up?
Yeah. Let's say.
Okay.
Okay. Are you doing the presentation or something?
Oh, yeah.
Just sit down. Then.
Great.
I'll be right back.
We may wait for 2 more minutes to get more audience. Abigail, do you have an idea like how long the presentation will be?
So it's 40 slides.
Yeah.
So maybe 40 minutes. And that works normally because you said like 15 to 20 minutes for questions.
Yeah. So that's it.
Okay.
Should I turn off the light or do we do it?
We can. 2 minutes.
There's one that is.
Should we post it? Okay, let's start now. So welcome to today's network seminar. And today we have Dr. Abigail Horn. So Abigail is currently a research associate in biostatistics in the Department of Population and Public Health Sciences at the University of Southern California. And before that, she obtained her PhD from the Institute for Data Systems and Society at MIT, where she focused on modeling food supply systems from farm to fork applications in food safety. The general area of her research is a combination of approaches from data science and systems modeling with emerging large-scale data sources to understand drivers of pricing, public health, and safety challenges that can involve future intervention. So now Abigail is based in California, so it's very early in the morning. So thanks for your enthusiasm. And now the floor is yours. Feel free to start.
Thank you. Yeah, thank you, and thanks for having me here. I'm excited to be here, even if it's a little early for me. And yeah, I'm looking forward to talking to you a bit about work that we've been doing using food supply networks, food system supply networks in the identification of large-scale outbreaks of foodborne disease. So I want to briefly acknowledge the great team that is part of this work. So we have Hanno Friedrich, Andreas Balster, and Tim Schleich at the Kuhne Logistics University in Hamburg, Germany. And then Marcel Furman and Matthias Filter, who are at the German Federal Institute for Risk Assessment, which is the German federal level food safety research authority, where I spent a couple of years at both of these institutions before coming to USC. And so we've been carrying out this work for several years now, and it still continues. So I like to start the talk by motivating the importance of studying foodborne diseases, large-scale outbreaks of foodborne diseases, which might seem a lot smaller than the kind of outbreaks that we're used to dealing with right now with COVID, but they're still important problems to solve. And with the industrialization of the food system, these outbreaks can just get larger and distribute more widely through the food systems, through across countries, continents, and global systems. So this particular outbreak is a good example of that. This is the 2011 outbreak of E. coli carried by, which was traced back later to be carried by contaminated sprouts. The origin was in a small organic farm in northern Germany, but thousands of cases spread throughout Europe and even into North America. The cases were imported by travel. And this was a very large outbreak, and it was scary at the time because a number of different food products were hypothesized as being the source, but the investigation timeline was such that while the outbreak was identified in early May, it wasn't until 6 weeks later that the food source was identified as being sprouts. And so over that time period, you can see that the majority of people that got sick from this outbreak got sick during this time period, and people didn't know if they could eat the kind of the products that were identified were a lot of common products like vegetables and salad and milk, some dairy products, and commonly consumed kind of cheeses. So yeah, this was a large outbreak, and it was frightening because people didn't know what it was. They didn't know what they could eat. And yeah, it took 6 weeks to identify the food source, and then it took an additional month or so to identify the location source at, like I mentioned, that farm in northern Germany. Although it's a little bit more complicated than that, because the seeds that were actually contaminated came from a seed producer in Egypt, which it was a very big networks problem to trace this back. And I'm not going to get too much into detail on that, but I wanted to provide a little context on this outbreak to give an idea of the importance of working on these problems, but also the scale of these large scale outbreaks that we're developing methods to approach. Okay, so these are very hard to trace to the source. And the common approach for identifying what I'm going to be talking about today, identifying the food item source of large scale outbreaks, is epidemiological studies. So it's called food recall case control studies, where patients who have been confirmed to be associated with the outbreak are interviewed. They're given like a 40-page trawling questionnaire with all these different questions about food They may have eaten in the previous 2 weeks, because it can take up to 2 weeks or 2 weeks before they had the onset of symptoms from the contamination. And these you can imagine that these kind of investigations are they're limited by recall bias. They're very time intensive. And another major issue is that they often return a large set of frequently consumed food items. So we saw these kind of problems, and we thought, are there any, how could we use data science, data-derived approaches to or more efficiently generate hypotheses about the food source origin? So we frame this problem as one of network source identification. So given several or a set of multiple network models of different food, the food supply of various food items, how do we identify the food type network that best supports the observed outbreak pattern? So this is kind of the general idea of our approach. And the way that we carried it out, we had to break it down into several different pieces. And so even though I'm talking about this third piece, which is identifying the food type origin, I have to start by talking about how we model the food supply network structure, because models of these large scale aggregated food supply networks, models or data on these large scale food supply networks is not readily available. While each company will have, major companies will have their supply chain mapped, their distributors and the follow-on parts of their supply chain. The aggregated picture across companies, this data is not readily available, and in fact, there are competitive advantage reasons why it's not shared with beyond the company. So we take an aggregated perspective on this, and we develop models of food supply network. And then, although I mentioned in the context of the E. coli outbreak, we first identify the food type source, and second identify the location source in the network. I have to explain how we identify the location source of the food item before identifying the approach for identifying the food type source, because the method for identifying the location source underlies that for identifying the food type source. So starting with the food supply network, I'm going to kind of go over this briefly because it's not the main piece of what I'm talking about today. So this is work that came out of CUNY Logistics University by my colleagues, and some work that we've done together. So the idea here is to develop we develop this spatially industrially aggregated food supply network structure consisting of these multiple stages of agriculture, production, processing, trade, and distribution, and consumption. And what I'm showing you on the left is a visualization of the network flows for the supply chain of vegetables in Germany. So this is roughly the shape of Germany for those of you that are familiar with Germany. And it's spatially aggregated into 402 county level regions in Germany, and 50 import-export countries. So we have nodes at each of these spatial levels of aggregation, and then across, and then at each of these levels of supply. And so in addition, so I'm not going to get into the details of how this is done, but essentially we use various data sources to map the aggregated nodes in each of these layers, and then we use a system of gravity models that are calibrated to federal transport plan data to estimate the links in this network. And we do this across, so that there's it's basically a system of networks, because we have all this set of, it's a set of the 51 food categories that some are quite aggregated, but across these categories, we capture all the food products that are produced and consumed. And so I'll talk more about this later, but essentially we have this network of networks of the food supply system in Germany. Okay, let's assume now going forward that we have access to these models of the network structure of the food supply system. With those network models, we then develop an approach for identifying location source. And so this is the problem of, yes, given this, here's a stylized view of that network structure. Given this food supply network, and then given reported cases of illness, people that have been confirmed to be associated with an outbreak and an outbreak strain, and their point of contamination is linked to the network by the point of consumption or purchase or consumption, be it a retailer or a restaurant or so on. I have in this example, retailer. Our question is, can we develop a model to give us the probability distribution over all feasible sources that could have distributed to all of these locations? And then if we have that probability model, we can also develop an estimator, of the maximum likelihood estimator of the source location. So this is, we can frame this as an inference problem, which if we have a prior probability, we can call it Bayesian inference. And the objective is to determine the probability that any feasible source is the true source given the observation set of illnesses that have been linked to the network, either at spatial locations or at specific points of consumption. And this is a problem that this network source location problem, it's been approached by various researchers in the last decade. We have this little review paper where we compare, where we look at these various approaches which have been developed mostly for in contagion processes and kind of the rumor spreading processes in social media. And we talk about why these existing approaches don't apply well to the foodborne disease context. And one of the main reasons that I'm going to draw attention to is that whereas a lot of these problems try to cut through the complexity of a network structure by assuming that the contamination will spread to the downstream nodes along a shortest possible path or highest probability path, and kind of ignores other paths beyond those shortest or highest probability paths. In food supply distribution, we have multiple paths, multiple candidate paths, we call them multiple paths of similar probability along which the contamination could travel. And so I'm showing an example here from, again, German system. And the map that I have on the left is colored by the cases during the 2011 outbreak, the E. coli outbreak. And we had a cluster of cases this is the source rather, circled at the top. And there was a cluster of cases down here in the Southwest. And if we look at the supply chain links to get from the source at this area called Ulsen in northern Germany to this outbreak cluster, we can see the width of the paths here. There are a lot of paths of similar probability to get from the source to the sink, and we need to be able to account for all these different paths in our approach. So, we do that by this is how we approach the source location problem in the context of foodborne disease. We develop a random walk contamination transmission model that accounts for multiple possible paths, which is really just simply we model the network as a Markov chain, and the transition probabilities in this network, in this Markov chain, are the relative flows exiting each node and going to a directed path. And it's an absorbing Markov chain because in the way that we're modeling the network structure, we have this layer of consumption where food is removed, never to re-enter again. So we have this absorbing Markov chain where we have transitions between transient nodes and then between transient and absorbing nodes. And with this absorbing Markov chain, we can look at what's the probability of starting from any source node and being absorbed at any downstream node. And so we can it's a well-known quantity, the absorbing probability in a Markov chain. And with that, we can bring that back into our Bayesian inference approach and identify the probability distribution over all possible sources. Now, we make a simplifying assumption where we assume that to get from any feasible source node to all downstream nodes, that these contaminations occur across independent paths. And this is a simplifying assumption because we can even see through this network that these circled nodes, they multiple path, there are paths that are shared to get to these nodes from the source node. But we've explored this simplified assumption, and it works well in simulation, but I am working with a colleague to relax that assumption. But anyway, with that assumption of independent paths, we can just circle over all contaminated nodes and look at the probability to get from the source to this observation node across all of these paths. And we get this this nice expression for the probability distribution over all feasible sources, that they are the true source. And we can also get the maximum a posteriori probability, or the maximum likelihood probability. And yes, the contributions of this approach in the context of foodborne diseases, that allows us to capture probabilities across all possible paths. And I'm not going to go into results here, but when we've explored this against some of the existing algorithms that look at the set of highest probability paths, like if you've heard of the network effective distance approach, the Brockman and Helbing approach, we're able to do a lot better than that approach in specific kinds of network structures that have that are very dense and have a lot of paths of similar probability. Okay, now moving on to the main component of this talk today, which is identifying the food type origin. And to illustrate this, I'm going to take from our network of networks, I'm going to take 6 products representing different food types, quite aggregated again. So we have cheese, eggs, milk products, meat products, poultry products, and vegetables. And our problem framing here is, given these different network models of the food supply, how do we identify we want to identify the network that best supports the observed outbreak pattern. And so the essence of our approach here is to look at the information that comes out of the probability distribution across feasible sources that we just talked about. And so we want to, the idea is that there is a lot more information or structure in a probability distribution that has a strong agreement with an outbreak distribution. Or no, sorry, I said that wrong. There's a lot of structure in the PMF that comes from tracing back an outbreak distribution that could have been generated from a specific network structure. So each PMF, probability mass function, results from tracing back an outbreak on a network, and the ones with more structure are the ones that come from networks where there was a set of paths in that network that could have given rise to the observed outbreak distribution at the contaminated nodes. And so I'm showing you an example here where on the left, I've simulated an outbreak on the vegetables network and traced that back on the vegetables network and traced it back on a different network, the eggs network. And we can see that there is a lot more structure in the PMF traced back on the vegetables network, because there are some nodes with very high probability. And so the true source is, at least through inference, we would assume it's maybe one of these nodes. It's in this cluster region here. There's some spatial element here too that we're picking up on, that we're not really seeing in this 2D representation, but we can see it here. So that's the structure. And then on the right, we have almost a uniform distribution where each source node that was traced back is basically equally as likely as every other node of being the source. So there's very low information in that distribution. So this is kind of the essence of what we do, but we have to capture it a bit more systematically, capture this amount of information. Oh, this is just the same view. If we rank order the probabilities, we can see it a little bit more clearly, the difference in the amount of structure in the distributions. Okay, so going forward, I'm going to refer to this PMF over feasible sources derived from tracing back an outbreak distribution on a network structure as this chi distribution. So it's basically this is just equal to the probability. What's the probability of a source given an outbreak set at contaminated nodes? And this outbreak set is of a certain size of illnesses. And we get a probability mass function as we've been seeing over these feasible source nodes. And then I also want to define for moving forward, we have 3 different types of outbreaks that I'm going to be talking about, and they have associated probability mass functions. So we have what I call the real outbreak distribution, which is the outbreak distributions in these 3 maps are that the outbreaks, the contamination cases are indicated by the red dots, and the shading on the map, the aerial shading, is representative of the probability mass function, the chi distribution that was traced back on a specific network given this outbreak pattern. And so here I have, this is actually from the 2011 E. coli outbreak. So these cases were the distribution of cases across Germany as of week 6, I believe, of the outbreak. And the shading on the map is the probability distribution that we traced back. And I call that the real outbreak. And then I can also simulate an outbreak on a network. So here I've simulated an outbreak on the vegetables network. We can see that there's maybe some higher clustering of cases in these certain areas. And when we look at the probability distribution, we can see that it's higher, there's a higher density in a certain region. And then here at the bottom, I've just taken a random sample of nodes and called that the contamination distribution. So you can see it's kind of like uniformly distributed across the map, these red dots. And then when I trace that back, I call that a randomly sampled outbreak just for convenience. It's not an outbreak, it's just a random sampling of nodes in proportion to the population of the contamination quantity at these locations, but it's not representative of any, it doesn't necessarily have a source that it could have been generated from. So we'll be talking about these 3 types of outbreaks and their associated PMFs, the real, simulated, and random. And then we can get back to characterizing the information in a distribution. So first kind of metric for characterizing information in a distribution that comes to mind is the entropy. And we have, for this example, this very stylized view of the probability distributions that I showed a few slides back, where we have a lot more structure in a certain distribution. We have a lower entropy, and where we have less structure, we have a uniform distribution. We have higher entropy because it requires more, in this case, it requires less information to convey what is happening in this distribution in a very simplified information theoretic explanation. And with this entropy, we can actually measure by simulating outbreaks on each network or doing these random sampled outbreaks on each network. We can generate these distributions and trace them back on each this set of 6 networks in Germany, and measure the entropy and see that each network basically has its characteristic entropy. So there's definitely some meaning in this ordering of different entropies of these networks. So here on the left, I have the distributions that were simulated on the outbreaks. that were simulated on the networks and then traced back. And on the right, it's the random sampled outbreaks that were pulled from a network and traced back as a distribution on each set of networks. And for both cases, we see this kind of systematic rank ordering, meaning that each network has its own kind of characteristic entropies, and there are these differences in entropies. And because of this reason, we can't just take distributions like we see here and measure the entropy and use that to compare network distributions. Each network has its own kind of characteristic amount of structure that we have to control for. So that's kind of the next step of what we have to do in developing this map. We have to control for that characteristic structure of each network. And that we have to control for that upper bounding structure that comes from the kind of the optimum amount of structure that we can get from simulated outbreaks, and the lower bounding amount of structure that we get from these from randomly sampled outbreaks. Because the structure and the rank ordering, if you can just tell from the colors, it's different across the network. So if you look at the difference between the upper bound and the lower bound for each network, it's different as well. So we have to control for both of those types of structure. And so then we can't use the entropy, but we use the relative entropy, the Kullback-Leibler divergence, to measure the information gain between several distributions. And specifically, we look at the simulated. We look at two types of Kullback-Leibler divergence. We look at the Kullback-Leibler divergence between the simulated outbreak and the random outbreak, and between the real. Oh, yes.
All right, we have a question from the room.
Yes,
Yeah.
Go ahead.
Yeah,
Sorry.
A few slides back, and we were having a bit of trouble to communicate, it seems. One slide back, please. Yeah, this one. So what is here on the vertical axis? Is that the entropy?
Yes. So one thing I kind of jumped over because it was a step that it didn't explain is that I actually took the inverse of the entropy. So the y-axis is the inverse of the entropy, and the x-axis is oh yeah, I really didn't explain this. So the x-axis is the number of cases that were contaminated. So let's say we had an outbreak of 500 cases. I can trace back that outbreak with the information available as of the first 1 to 100, 500 cases. And so this is showing, so at each of those points, I trace back the outbreak and I get a PMF, and I measure the entropy of that PMF, and then I save the inverse of that entropy. So, and then I do that for each, each number of illnesses and each network. Is that more clear now?
And does it make sense that for a small number that you get these higher values, or is it not really important?
Yeah, good question. Yeah, it's just this kind of if I zoomed in and I just showed between 0 and 10, what you'd see like this. You'd see this very unstable signal because it's with two cases or something. You might see there's a good explanation. There's a very strong explanation to get to these 2 cases, and so that comes up as a very high point after 2 cases, and then it jumps down and jumps up. So it's in its unstable period.
Yeah. So the thing you said, this characteristic entropy is more when there's more numbers, then you're more sure about it.
Exactly.
Yeah. Okay, thanks.
Thanks.
Yeah. Thank you.
We have another question. Sorry.
Okay. Good. Yeah.
Yeah. Sorry. I think there's something I don't think I understood. When you when you do the simulated outbreaks, how do you choose the sources?
Right. Another good question. I didn't explain that at all. So we just randomly choose. So we just randomly choose different source nodes. We sample according to the amount of product that is distributed by, if we have a prior probability distribution, we'll sample according to that distribution. But if we don't have a prior probability distribution, we just sample at random. And I didn't make this clear either, but I'm going to go back a few slides to get a network picture. We assume that the network source is in this first stage of production. Now, in practice, that is almost always the case with large scale outbreaks, because to be able to transmit to multiple downstream paths that with contamination occurring in a very widespread manner, that can often happen across that requires this very large network along which it can be distributed. So we're never looking at something that happens at point of contamination. We're looking at these large scale outbreaks. But of course, you can definitely get outbreaks that happen at this point of processing, which the method is able to account for as well. But we simplify it in this paper and just look at outbreaks that could have started in this top layer.
Thanks.
Yeah, good question. Thank you. Okay, so we see each network has its characteristic signal, and we need a control for that through the upper bounding and lower bounding. And so we measure 3 types of Kullback-Leibler divergence. We look at the divergence between the simulated PMF and the random PMF, and between the real PMF and the random PMF, because we want to be able to control for both the upper bounding and the lower bounding behavior. So we look at these 2 types of comparison, and then we take the our method just looks at the ratio of these 2 types. So the Kullback-Leibler divergence that we got from the real outbreak compared with the random outbreak, the random sample outbreak, and that one that we got from comparing the simulated outbreak and the random outbreak. And you know, I cut out a couple slides because I didn't know if I was going to have enough time, but I kind of want to show a diagram of this. If I can just end my presentation for a minute. You still see my screen, and then let me unhide this. So sorry. Oh no. All right, there. Thanks for bearing with me. So this is a visual of what we're doing. So we get this, ultimately we're trying to get this normalized signal detection approach. And so for each network, we have, so we have a single real outbreak that we're trying to investigate. And with that real outbreak, we trace that real outbreak back on our set of candidate networks. Here in this example, we have the vegetables network and the eggs network. And we compare, and that's where we get this real PMF from tracing back the real outbreak on here, the vegetable network, and here the egg network. And we compare that to tracing back a random sample outbreak on each network and a simulated outbreak on each network. And so we can see pretty clearly in this little example that when we simulated an outbreak, that the real network, the real outbreak came from the vegetables network. Because when we look at the amount of information, so what I'm showing you here, this is this bar graph that's been rank ordered, and just the structure of that it is just shown as a line plot. So it's showing the same information here, but as a rank ordered line plot. And we can see that there's a very similar amount of information or structure in the simulated outbreak, the PMF that came from the simulated outbreak and the PMF that came from the real outbreak, and that there's a lot less structure in the PMF coming from a random sampled outbreak for the vegetables network. And then for the eggs network, we see that there is a lot of structure in the PMF that came from the simulated outbreak on the eggs network, because it was simulated on a network, but the structure coming from the real PMF that was simulated on the eggs network, or the real PMF that was traced back on the eggs network has very little information. And so that's then with that, I mean, we can see here clearly who the winner is, but to quantify this, we take the Kullback-Leibler divergence between the simulated PMF and the random PMF and the real PMF and the random PMF. And so we see similar Kullback-Leibler divergences in this example for the vegetables network, and very different Kullback-Leibler divergences. This plot is just showing the Kullback-Leibler divergence for each of these networks. And so then the final step to get the normalized signal detection metric is to take the ratio of the Kullback-Leibler from the Leibler divergence from the real outbreak to the simulated outbreak. And here we get something close to zero, but not quite zero. Okay, so that's the whole idea, and then we can evaluate it. We can evaluate it on stylized networks. So here I've generated a set of 6 networks, and we can expand this simulation example, but for the case of illustration, generated a set of 6 networks that have this kind of structure. I call it a random layered graph. We have a graphing library for these kinds of random layered graphs, and we generate links. In the networks that I'm evaluating here, we have I've used 4 stages of supply, and the flows are directed across these stages. They can jump stages, but most of them are from one stage to the next. And it's mostly a partite network. And to sample the weight of the number of links coming out of a node and the weight of those links, we use geometric distributions. And so we get something that we look at the distribution, the link distribution and the weight distribution, we get something that approximates what we've seen in real food supply networks. But this stylized network allows us to control the size of the network and do a lot of simulation experiments. And so we've used that to evaluate the accuracy of the approach. And the accuracy, I'm showing 2 metrics. So I've simulated on these types of networks, I've simulated hundreds of outbreaks and traced them back on this set of 6 random layered graphs, and then applied the normalized signal detection approach on each of them. And I can evaluate the accurate, I can remember which was the network that I simulated the outbreak back and trace that back, and look at the accuracy of the approach according to 2 metrics. The accuracy, which is quantified as if the true source or if the source network was in the first position of was in the first ranking. If I identified the source network, then accuracy is 1. And if not, it's 0. And I look at that across the number of outbreaks. And on the left, I have the rank, which is just the position of the true source in the ordered ranking across this set of 6 networks. And so the rank is very low for the true source, and the accuracy is very high on these stylized networks. Then I can do the same simulation experiment on the Germany networks. Oh no, I think that slide. Okay, I'll have to come back to that slide. I'm gonna just jump to the implementation for the E. coli outbreak. So back to this that we saw at the beginning of the presentation. This is the epidemiological curve for the 2011 E. coli outbreak carried by contaminated sprouts. So we wanted to see here if retrospectively, like a decade after, we could identify the source network, the source food item. And because we have these very highly aggregated networks, we want to be able to identify the vegetables network, because that's what sprouts are, a vegetable and distributed more like a vegetable. So we want to be able to identify the vegetable network as the true source network. And we want to compare it to these various other networks that were implicated as hypothesized food type sources early in the outbreak. So we have here meat products, milk products. So some of the food items that came out of these early case control studies were yogurt, fresh cheese, and other types of dairy, quark, for those of you that know German dairy products, and then meat products, and then various meat products were also identified. And again, it was this set of hypothesized food sources was identified around week 3, and sprouts were confirmed as the source, like I said at the beginning, around week 6 of the outbreak. And so with our model, we were able to see by the information of week 2 of the outbreak that these 2 networks came out on top. So I think I should describe this figure a little bit more clearly. So this kind of looks more like what I was showing with the entropy figure, where I've traced back the outbreak with the information available at an increasing number of illnesses that are rank ordered by their that are ranked by their timing. So I can trace back the outbreak at this time, at this time, at this time, at this time, with the amount of information that was available at those times, and that corresponds to a certain number of illnesses that have been reported. And I trace that back, and then I apply the signal detection method that I've just been describing. And I do that to the set of 6 networks that I've been considering, because part of the reason I'm considering those 6 networks is because many of them were implicated in the context of this outbreak. And we identify these two networks with similar entropy, normalized signal resonance entropy metrics, the meat products and the vegetables network. And so the meat products network had a slightly higher score than, consistently slightly higher than the vegetables network, which the meat is green, the vegetables is yellow. But still, this kind of clearly identifies these 2 networks and the associated food types as being much more likely to be the source than these other networks that are under consideration. And so I think just looking at this figure, so the kind of the main limitation of this approach, or it's work in progress. So, but limitation where it's at right now is this is what we get as a result. It's a qualitative comparison across these different networks that could have with metric scores across these networks. And we've looked into quantifying this a bit. Is this network that much better than? I mean, we can look at the ranking of these networks, and I didn't I may not have described that very clearly, but that's what we did with the simulation accuracy tests from the previous slide. We looked at the ranking of these. We also looked at some like some different tests for different algorithms for kind of quantifying what the source was. But I think where the science currently is, we don't have enough. Most cases when we're looking at a single outbreak case, it looks something like this, where we have strong negative information and strong positive information. And so I think we need to have a larger set of real outbreaks to be able to evaluate this approach on and develop more quantified measures of which network is the true network. So yeah, this is what we get from our output. And so so that is what we have on that. I was going to also show, now that we have identified the source network as vegetables, then we can apply the location source part of the approach that underlies this. So identifying the probability, the source location in that network that is the source network. And so we take the vegetables network and we trace back the outbreak on the vegetables network, and we were able to look at the probabilities. I showed this figure earlier, but we have the red dots are the outbreak cases across Germany, and the shading on the map is where we have counties that have higher probabilities of being the source. And when we look at that bar chart, you see it on the right here. We see there are some of these counties that have much higher probability than other locations, and the true source turns out to be at this location and this bar. So so that's what I have here. And I think, just to summarize, like I said, this is a work in progress, but it represents the first approach to use the information inherent in the food supply network or the food supply network models to identify possible food sources of an outbreak. And the network models that we used, that I didn't talk about in too much detail here, but you got an idea of what we're doing. They're very aggregated and they're estimated through gravity modeling and so on. But I think it's been really exciting for us to see that our case studies, like the one that I showed with the E. coli outbreak, suggest that it can provide meaningful information for distinguishing between possible food type sources. And something I didn't get into too much is that these food networks are structurally unique, and it's important to consider these unique features in the source identification problem. So we saw that with the characteristic entropies for each network, and there's definitely a lot more work to be done there to look at what is it that leads to those characteristic structural differences in each of these networks, or it's the structural differences in the networks that lead to different characteristic entropies and accuracies when we simulate and trace back outbreaks on those networks. So we looked at that a little bit. We looked at these various metrics across each network: the number of producing nodes, the in degree, the out degree, the strength, and the entropy of the degree distributions. And we did a little correlation analysis, and it looks like certain networks are more predictive of the characteristic entropies of each network, but it's really not. We can't look at individual metrics. It's a combination of networks, and the combination of metrics and the structure of the network that gives rise to this. So I think there's some opportunity for a learning type of approach to look at the relationship between the network structure and the characteristic structure, the characteristic entropy of the network, and so on. And I'm going to jump over this. We've done some work on that too, but so yeah, I think I'm going to just end here, and we have several minutes for questions. Stop here.
Is there any question from the room?
So I couldn't hear. Can you relay the question?
You can come here and speak. That might be easy.
No.
No.
Oh, it's really like distorted. It's still really hard to hear, but I feel like I could make it out now.
So I'll make it brief. So
Okay.
it's just about the comparison in the X network versus the vegetable networks. It seemed when you plot the PMFs that you could use Spearman rank correlation, and that would give you a high value.
Okay, so Spearman rank correlation between sorry, I didn't quite hear the first part.
In the PMFs of
Yeah.
Simulated and simulated and real, or
Okay.
real, we're comparing source versus eggs.
Yes.
You use the instead of the
Shoot, I can't hear you, but I think I got the gist of it, and so I could explore the Spearman rank correlation, and that's not something I've done at all, so that's great. Thank you.
Can you hear me?
Okay, I can hear you. Yeah.
That's odd. Would you like to unmute yourself and speak your question? Or
Hello.
Oh, hi.
Hi. I can hear Abigail just fine, but hearing you is a bit difficult. I think it's a bit, robotic, the voice. So I don't know if you're calling on me, and I hope I'm not interrupting anybody else's turn. Okay. So my question is to do with the KL divergence, the sort of the metric that you use. I know at the end you say there might be some additional metrics you might want to learn for these networks, and you go over that slide with some correlations. I was wondering how the KL, did you investigate any areas with, say, especially sparse networks or things with really small samples in those cases? So, for example, diseases which might be quite deadly but not spread quite as much.
Yeah, so that's a very good question. So we did look at some spatially local outbreaks, but a criteria for being able to apply our approach is that there is a diffusion pattern that occurs across all of this. Well, it doesn't have to occur across all of the stages of the network, but it has to be what is constituted a large-scale outbreak, which in our case, practically, it's kind of defined as a multi-state or a multi-county outbreak that takes up a large part of the network. So I have to admit, we didn't do too much testing on small of very small and localized outbreaks, partially because we're looking at these large scale outbreaks. But then you're also asking about very sparse networks, which so we've kind of designed this approach to look at the kinds of food supply networks that I was talking about here. In theory, it should be able to be applied to something that's, you know, if we had, and I say this, I talked about this in the discussion of the paper. So what happens during an outbreak investigation is that investigators will collect information on the, you know, they'll get the parts of the supply chain that they'll trace it back from case patients, and they'll collect information from distributors and so on and put that together. And so in theory, the method should be able to, so they're getting these the dedicated supply channels that were potentially associated with the outbreak, but they're just getting like a snapshot of the supply, but it's still they're still getting a network snapshot. And so in theory, we should be able to apply this to those kind of settings. And I looked at that with some of the stylized networks, like the random layered graph that I was showing, but that's something that I haven't explored in a lot of detail. And so what you're suggesting is that the Kullback-Leibler divergence will not hold as strong when we get to really sparse cases. Is that kind of?
Yeah, like I at least in some areas I've seen that it performs differently when your samples start to get quite small. So in this case, I mean, that might correspond to a sparser network where spread isn't possible, or highly localized cases where I imagine the pathogen is either not as virulent or, you know, very deadly. It's sort of like COVID versus, you know, the earlier SARS cases.
Right.
Right. So interestingly, you also mentioned the sort of temporal aspects of this thing. Have you looked at things which are a bit more ephemeral? So things where you might get, where you might not be able to see where the cumulative distribution of a particular spatial patch may not be as representative of the actual behavior.
So that's a really well-informed question. I think so with these kind of outbreaks, we have when cases get sequenced, we can see what part of the genealogy they come from, and we can see the genetic evolution and know like kind of what order they came, and we'll often see these kind of outbreak claves and be able to associate certain, there can be like multiple stuttering outbreaks that occur with a single with a strain that is evolving. And so we would kind of because we are not directly looking at the spatial component, but that kind of underlies the distribution along the supply chain network. We would look at kind of each of those individual claves as its own outbreak, and trace that back. Now we've separately developed a temporally based approach for doing this whole inference process, but we can't apply it in practice at all because we don't have information on we don't have good data on the time delays through the various parts of the supply system. And furthermore, that's because there's a lot of uncertainty. So we can get these distributions with very wide with huge variance for the amount of time that the product would stay at each stage. And if you're adding all of those variances together across the steps of the supply path, it's too much variance to be able to identify, to use that information to help identify the source. But I think your question was more intricate around when you see this kind of pattern that stutters and leaves. I mean, if I go back a few slides, you kind of see that happening a bit with the E. coli outbreak, where you see like that pattern losing structure.
I think the room is booked for the next hour.
Okay.
So probably. Okay.
I did have a question, but I guess we can't do it.
Well, thank you for a really nice talk. I hope is there. I didn't catch an email. Is there an email at the end of the slide?
Yes,
or something I missed?
yes.
Yeah,
I had. Please follow up with me. I should have left my email up here. Please follow up with me. I'd be really happy for all of these questions and insights. Are really, really helpful. So
just before we do finish, have you thought about within kind of ecological networks, there's a method known as trophic analysis, which looks at the flow of energy from your suppliers, like your prey, up to the predator. And have you looked at applying that to I always thought the food supply network would be a good analog to it.
So what would be the question? What kind of source